On November 1, 1952, the United States detonated the world's first hydrogen bomb on a small coral island in the Pacific Ocean. The explosion vaporized the island entirely, leaving a crater 164 feet deep in the ocean floor. Hours later, military jets flew through the radioactive cloud, scooping up debris in specially fitted filter tanks. What came back in those filters was unexpected. Hidden inside the fallout of the most powerful weapon ever detonated was an element that had never existed on Earth before. The test was code-named Ivy Mike. It detonated with a force of about 10.4 megatons, around 700 times more powerful than the bomb that had destroyed Hiroshima 7 years earlier. It was in the fallout from Ivy Mike's explosion, amid the chemical debris, that atomic number 99 was found for the first time. The group headed by Albert Ghiorso at the Lawrence Berkeley National Laboratory discovered that the bomb blast had created isotopes of new transuranic elements by intense neutron bombardment of uranium. The discovery remained secret for a number of years as the data fell under classification owing to the military importance of the test. When declassified, the findings were published in 1955. Einsteinium has atomic number 99, deep in the actinide series at the bottom of the periodic table. It is synthetic. It does not exist in nature, and never has. 1 gram of Einsteinium produces 1,000 watts of energy. It emits harmful gamma rays, so working with the element requires researchers to wear protective gear at all times. Its most commonly occurring form, Einsteinium-253, has a half-life of only 20 days, meaning that after 20 days, the sample decays by half. Annual global production is estimated at less than 1 milligram. Only a few milligrams exist on Earth at any time. The radiation is so intense that it physically degrades the sample over time, damaging its own crystal structure. For nearly 70 years after its discovery, almost nothing was known about Einsteinium's chemistry. The half-life was too short. The radioactivity was too intense. Samples degraded before they could be tested. That changed in 2021. A team of chemists led by Rebecca Abergel at Lawrence Berkeley National Laboratory used modern experimental tools that scientists decades ago simply didn't have. With less than 250 nanograms of Einsteinium, they carried out the first study to directly measure some of its basic properties, including the first-ever bond distance of the element. Their findings were published in Nature, but the work almost fell apart when the COVID-19 pandemic shut down the lab in the middle of the experiment. While they were locked out, about 7% of their sample decayed every 30 days. By the time they returned, much of it was gone. But they still managed to finish the study. The team also found that Einsteinium behaved differently than expected compared to other elements in the actinide series. That discovery could help scientists better understand the heavier transuranic elements that come after it. Even in amounts too small to see, Einsteinium is still changing how we understand the periodic table. Here is the detail that makes the naming genuinely strange. Albert Einstein was one of the most vocal opponents of nuclear weapons on Earth. He never worked on the Manhattan Project directly, but in 1939, alarmed by reports of German nuclear research, he co-authored a letter to President Roosevelt warning about possible German nuclear weapons research and urging the United States to start its own atomic energy program. That letter helped initiate what became the Manhattan Project. For the rest of his life, he viewed that as a profound moral burden. Einstein's final public act before his death was co-signing the Russell-Einstein Manifesto, a declaration co-signed by 10 of the world's most prominent scientists and Nobel laureates, which decried the likely spread of nuclear weapons and called on world leaders to renounce war as an acceptable method of resolving disputes. He signed it days before his death in April 1955. The element named in his honor was announced publicly that same year for his revolutionary contributions to modern physics, especially his work on matter and energy. It was also born directly from the weapon he spent his final years trying to prevent the world from using again. Einsteinium has no practical applications. Due to the small amounts produced and the short half-life of its most common isotope, there are no practical applications for it except basic scientific research. It cannot be used in medicine, industry, or energy. Only tiny amounts of it exist, just micrograms, and it decays within weeks. Scientists have only studied it seriously once, in a 2021 paper that used a sample smaller than a grain of pollen. Even so, it carries the name of the person who helped shape the 20th century's understanding of energy and matter more than almost anyone else: Albert Einstein. He understood not only what physics could reveal, but also the price humanity might pay for unlocking that power.